Thank you very much. Thank you very much for the nice introduction. I'm happy to be with you here, at least via streaming. I would love to be with you. Hopefully it will be possible next year. But this year we will try to make the best out of it by streaming here from this beautiful town called Leonding near Linz. I am from Austria. My name is Rainer Stropek and I'm looking forward to 45 minutes about WebAssembly, about Rust, and about TypeScript. I said that these three technologies are made as a match. It's a match of heaven. Yeah, I really believe in these three technologies. I believe in the great future of these three technologies. And in the upcoming 45 minutes, I want to show you why. And that I will do without any slides. I will really focus on code. You will see a lot of code. You will see a lot of samples. We will do some things live. Some things will be more like a code walkthrough. We will try to make the best out of it, to make it a fast-paced and demo-heavy session. Before we dive right into the first demo, let me tell you a quick story for those of you who are not that deep into WebAssembly. What is this WebAssembly thing? You see, many years ago, some people came to the idea that it would be really nice to use their existing, mainly C and C++ code base just right into the browser, because the browser is everywhere. JavaScript runs everywhere. C, C++, it runs everywhere too, but many people don't want to download some compiled code from the internet and run it locally because of security issues. So the point is, those people thought it would be a good idea to compile C and C++ code to JavaScript and then run it through JavaScript in the browser. This project was called emscripten, and it was the early beginnings of WebAssembly, of the WebAssembly idea. Now, mainly the Google guys, the guys that worked on the V8 engine, saw this project and they found it interesting. They took a look at the generated JavaScript code, the code that was cross-compiled from C and C++, and they thought, hey, we can make that better. So they optimized the V8 engine to specifically run cross-compiled code in a very fast way. And out came ASM.js. This was also a kind of step towards WebAssembly. ASM.js already proved its power by running things like SQLite in a browser, by running game engines in a pretty fast way inside of the browser, so the concept proved its value. But when the engineers took a close look at all this JavaScript stuff, they figured out that essentially what this thing is doing is it's simulating a linear memory based on a JavaScript array. That was the memory, and then everything else was rather bulky JavaScript. It could be executed, nobody would write it in this way, so a big advantage of JavaScript, being humanly writable, was no longer relevant. And from that idea, WebAssembly got started. So WebAssembly is a really virtual machine, a very low-level virtual machine with a linear memory like a real computer. Its instruction set is rather simple. Its data types are rather simple, so very near to assembler language, and but everything else is very similar to JavaScript. You can download WebAssembly from the web. This is why it's called WebAssembly. You have a very small and thin engine that compiles the virtual machine code to real machine code. So that thing of getting it started, doing the just-in-time compilation after downloading this stuff, is also very fast, much faster than JavaScript. So what we got is a possibility to cross-compile C, C++, and so on to a binary standard, this WebAssembly stuff, and the browsers will no longer get JavaScript and optimize that one, but they will get a binary low-level virtual machine which they can execute safely inside a sandbox inside the browser. Now, what did that do? It ended the monopoly of JavaScript in the browser. No longer is JavaScript the only real programming language inside of the browser, but now we can take any language that is able to use WebAssembly as a compilation target and run it inside the browser. So now suddenly we can take C code, C++ code, we can take Rust code, we can take Go code, we can take .NET code, we can take Java code, and we can compile it to a virtual machine, a low-level virtual machine, this WebAssembly stuff, and run it directly in the browser. That's the idea of WebAssembly, and that sounds very interesting because JavaScript is super useful, but one thing JavaScript is not. It's not the fastest platform on earth for doing compute-heavy calculations. This is not something where the sweet spot of JavaScript is, and this is where WebAssembly really shines. Don't see WebAssembly as a replacement of JavaScript. That's definitely not the case. WebAssembly is more or less a low-level virtual machine, I repeat myself consciously, and it's super fast when it comes to compute-heavy calculations. Think of games, think of visualizations, think of audio processing, think of video processing, cutting videos inside the browser, calculating some codecs, for instance, doing some mathematical calculations for maybe a CAD, a computer-aided design system, or some visualizations for architects and things like that. In all these areas, WebAssembly is really, really fast, and it has proven to be fast, and it has proven to be faster than JavaScript. Now, we have that story. We know what WebAssembly is really good at. What about Rust? Rust is today the #1 language when it comes to WebAssembly programming. Why? Well, Rust is capable of doing systems-level programming. It's blazingly fast. You reach the performance goals of C and C++ with this language, so it's really fast. But why should you consider Rust and not going directly towards C and C++? The answer is simple. Security and safety, memory safetiness. You know, endless studies have shown that the majority of security flaws is related to memory issues. Double free. You free something although it has already been freed. Use of the free. You access memory after it has already been freed. And many other things are typically bugs inside of C, C++ code. Why? Because those languages do not really protect you from making a lot of mistakes. Managed languages like JavaScript, like Go, like C#, like Java, they can protect you to a certain extent because they have a garbage collector and they have managed memory. Not so C and C++. But those managed languages, they pay. They pay a price for having that memory safetiness, and this price is performance. So what Rust can really do is it can give you the memory safetiness of a managed language, and even better than most managed languages, while offering the same performance as C and C++. And that is really awesome, because that means our compute-heavy calculation algorithms will be safe. They will no longer have some race condition when it comes to multi-threading and things like that. And they will be as fast as when we write the code in C or C++. And now combine WebAssembly with Rust. Safety, performance, and a platform that can easily download code from the internet and access it securely in a kind of sandbox. And with that, we can really raise the browser to a new level. We can do things which weren't possible before in the browser, especially when it comes to compute-heavy things. But don't see WebAssembly just as an enabler for new things. It is also an enabler for bringing existing stuff into the browser. Think of FFmpeg. You can do video editing with FFmpeg, with the existing code inside of the browser. You can use existing algorithms, existing game engines for visualizations, or CAD systems, and many, many other things. So we can take existing code and bring it into the browser. This will not be a topic of this talk, but you have to keep that in mind when you think about what is WebAssembly really good for. Well, I said 3 things are a match in heaven. WebAssembly, Rust, I described that. What about TypeScript and JavaScript? Will WebAssembly remove the need for JavaScript and TypeScript? No, it will not. Because WebAssembly is very low level, and there are a lot of things which you can't do today in WebAssembly. So WebAssembly needs a good friend, and this good friend is JavaScript. Whenever WebAssembly wants to talk to the user, wants to talk to the network, wants to talk to the DOM, we need to go through at least a thin layer of JavaScript. In practice, this layer is not so thin, so we need JavaScript in order to make WebAssembly really work in real-life applications. So we have really a friendship. We have a friendship of WebAssembly and Rust and JavaScript, and both work together. And this is exactly what I would like to show you. So now you know what WebAssembly is all about, why Rust is interesting, and that JavaScript and TypeScript will, at least in the near-term future, not go away. Now, let's dive into some samples and let's see how that works. Okay, so let's move my image here a little bit, make it a little bit smaller, because now we are going to do some demos. I'm here in my Windows subsystem, Linux subsystem for Windows, Windows subsystem for Linux, I'm sorry. And what I will do, I will start with a Hello World example. Okay, so I will run a tool which is called Cargo. Cargo is the build system for Rust. It's like NPM. So if you are familiar with JavaScript and TypeScript, that's your NPM. It's the dependency management, it's the build system, it's the system with which you alter your projects and things like that. That's Cargo. And here I'm using the official Wasm pack template. Wasm stands for WebAssembly. Pack, of course, we are packing everything into WebAssembly, and this is the template project. Let's call it Hello Wasm, okay? Oh, hello. Sorry. I will stop that one, run it again. Hello Wasm. Okay, now we have our project here, and I will open it up here in Visual Studio Code. I'm going to use Visual Studio Code as my primary editor, and I hope you can see everything fine. I can delete some files which were only generated for, I don't know it, I don't need them here. And we'll take a look in the code. You see, in a typical Rust code, you have the source code here in the source folder. If you are using WebAssembly and Wasm pack, you have a separate folder which is called tests, where you can add your unit tests. I only have 45 minutes today, so I will not dive into unit testing, but to make it short, if you are familiar with things like Jest, for instance, or Jasmine and Karma, this works very similar. So essentially you write tests. These tests are also WebAssembly, but they will run inside the browser. And you can spin up a test server. You can use any browser, serve to this web server, and it will execute the WebAssembly based unit tests inside of the browser of your choice. Very similar to Karma, Jest, Jasmine, and whatsoever. Now, this thing, it might look familiar if you take a look at it. It looks a little bit like a package.json file, right? And this is exactly what it is. You have some metadata, as you can see it here. The current edition of Rust is no longer 2018, it's 2021. Last Thursday, the new edition 2021 came out, so I installed it already for this talk today, so I can easily switch that here. And then we see also some things that I'm not going to talk about today because I only have a short session. But what I would like to show you is this one here. You see the dependencies? These are the dependencies, and this works very similar to what you know from package.json. So you see, this cargo toml is like our package.json. And in this case, we are referencing a library which is called Wasm bindgen. Now, Wasm stands for WebAssembly, obviously. But what is bindgen? Well, bindgen is the binding generator. Binding generator means it takes Rust code and converts it to WebAssembly, but in addition to that, it generates a JavaScript layer which helps us to call our code, and TypeScript type definitions which make our access to Rust from TypeScript type safe. So Wasm bindgen, I always call it Harry Potter programming. This is the fairy dust that you sprinkle over your Rust code, and suddenly you get TypeScript and JavaScript and a WebAssembly file, and you can immediately access your Rust code from within the browser. Awesome, isn't it? What we additionally get, we get a bunch of helpers. For instance, this one is an interesting one, console error panic hook. That makes sure that we get nice and complete error messages when we screw up in Rust. So if we have a so-called panic in Rust, that would be a very critical error, then we will get a nice stack trace with a nice message and everything like that. If we remove that dependency here, then we would not get a nice message, we would just get a message that something bad has happened, something in that ballpark. We could add a lot of dependencies which I will not talk about today because essentially they are for optimizing, and we are not talking about optimization here. This would be the dependency for running the unit tests, and I think the rest is, you can guess it from the context. So now we have seen that we have the source code, we have the tests, we have something like a package.json, which is now called cargo toml. So let's compile this stuff, okay? So we can run cargo and use build. this would be like npm run build, something like this. This will now go and fetch all our dependencies and compile it on our computers. Let me give you a little bit of a background information for those of you who are not that familiar with Rust programming, okay? What Rust does, it's pulling the dependencies from a website which is called crates.io. Crates.io is like npm for JavaScript and TypeScript developers. There we find all our so-called crates. This conference is happening in Germany, so I will quickly translate it. Crate is a Kistenverschlag. Crates are what you know as node packages, okay? So it will fetch all the crates, but it will fetch the source code, like in JavaScript, but then it will compile all the crates to binaries, of course. And at the end, we will get here in the target folder, in the debug folder, because we are now working in debugging, here a so-called dynamic library. This is a dynamic library for Linux. Is this WebAssembly? No. This is not WebAssembly. This is just to prove the point that I can take this code and compile it to native machine language. This is a library that I can immediately use in Linux, and I could also do the compiling on Mac. I can also do the compiling on Windows. This is machine code. And that is one of the most important things. Rust is such a great language, and more people are using this stuff to build not just web applications, but also server applications, desktop applications. And with having the possibility to move Rust with WebAssembly into the browser enables you to compile your code on the one hand side to a real binary for a certain compilation target like Linux, Windows, and so on. But you can also, and that is now the important part for our talk, instead of cargo build, say Wasm pack build. Wasm pack is a thin layer on top of cargo, and what Wasm pack will do, it will compile your Rust code for the WebAssembly compilation target. And now suddenly the target folder is no longer relevant, but we get a package folder. And guess what? Here we have the same code as a WebAssembly file. So now by adding this small layer on top of cargo, we can now compile not to machine language, but to WebAssembly, to this low-level virtual machine. And in addition to that, we also get a bunch of JavaScript, which is again a thin layer for calling into our Rust library into WebAssembly, and we get TypeScript type definitions, as you can see it here. For those of you who are really experienced JavaScript developer, you might recognize that this folder, in fact, looks very much like an npm package, doesn't it? It has a package JSON, and if you take a look at this package JSON, we see things like, what do we see here? We see that we have a module here, and we have some types here. So it looks like this is really an npm package, and that is exactly what it is. If you use Wasm pack and you compile your Rust code, what you end up getting is you get an npm package. And you can take this npm package, you can publish it on an npm feed, somebody else can consume it, you can reference it locally by specifying the folder name and all these things. All these things you get when you call Wasm pack build. Now the next step, obviously, is consuming this stuff, right? So let's try that, okay? Let's try consuming our library, and we will do that by creating a folder, .dub. And inside of the .dub folder, I will use the official, let me move that a little bit here, I will use the official template from Wasm applications. You see it here, and what we get, isn't that nice? Rust plus WebAssembly is love, and that's exactly what I think. Okay, so let's take a look at the code that was generated here. This is now a regular JavaScript application as you love it and you know it, and so on and so on. So if we take a look at the package JSON here, what we will see, as you can see it here, is we'll see a bunch of dependencies. And what we can add here, let's add it as a dependency. As a dependency here, we can add our hello Wasm. This is exactly our dependency that we had up here, and we will use a file one folder up and go into the package folder here. So we will navigate here, see, into this package folder, and we will reference the npm package that we generated from our Rust code. That's essentially all that we have to do. So do an npm install. That will only take a moment. And if we take a look at the www folder and look into the, oh, let me see. Oh, sorry. I screwed up. Unfortunately, I created another folder layer here. I wasn't. This just happened. I'm sorry. Okay. So npm install again. Now it takes a little bit longer. I messed up with the folder structure, but hey, this is just an example. We will switch to a larger example in a second. That looks good. What you see is that you get a lot of vulnerabilities and so on. To be honest, the templates that you find on GitHub are not fresh. I mean, take a look at this here. It's old Webpack. It's the old Webpack development server and so on. But don't worry, in this talk, I will immediately after this Hello World demo, I will switch to my own template project, and there you have the newest Webpack, the newest TypeScript compiler, the newest Webpack dev server, everything. But this is just the Hello World demo with the templates that exist, and nobody uses them. But it's good to demonstrate the core principle here. Now let's take a look in the Node modules folder, and if we are lucky and we go to where is it? Hello Wasm, we will see that we now have a symbolic link into our package folder that we generated from our Rust code. Here it is. This is our Rust code. So now we can use our WebAssembly stuff directly in our JavaScript code. Let's try that. So let's go into index.js. Here it is. I think I called it hello wasm, right? And here you see a call, a method which is called greet. And now let's take a look at the Rust code, and I think I do not really have to describe to you what's going on here. See, here is the call to greet. Here we see a Rust method. This is how you write a method in Rust. You simply say pub for public, fn for function, and greet. And then we use the alert function, and the alert function is an external function because it's a global alert function. It's the alert function of the browser. Please recognize that we have a wasm bindgen macro. This is a macro, so let me emphasize that. If you haven't programmed with Rust before, believe me, macros are important. Macros are really, really important, and you use them all the time in Rust. And this is a macro, a wasm bindgen macro, which tells the Rust compiler or the Webpack tooling that it should generate JavaScript code that makes it possible to call this function from within JavaScript. So this is what we essentially do. We call this method here from this JavaScript stuff. So I would say, let's give it a try, right? So bang, go into the, yeah, looks good. So start it. Okay, looks good. Run it. And it opened here on my second monitor, and see, great. Hello Wasm. So it worked. And if we take a look at what's going on behind the scenes, oops, I didn't want to do that one. I want to do that one, and take a look at the network here, reload our app. Okay. And you see that we now here get the bundle from Webpack, and here we see our WebAssembly, and this WebAssembly stuff was generated from our Rust code. So it's really not complicated. From this first demo, what you should take away is that you take your Rust code, and Rust is an awesome language. It's so fast, it's so secure, it's so safe, it's memory safe, and it makes you really productive. You take this Rust code, you use Wasm-pack, and what you get is an npm package. You simply reference this npm package, and off you go. You have JavaScript for JavaScript development, you have TypeScript type definitions for type-safe access to your Rust code, and you're good. You can start coding. So this was the first introduction. I wanted to take approximately half of the talk, and I think I managed to do that. I wanted to take approximately half of the talk to show you the basics and to make you understand how the principle works. But as I said, to be honest, this stuff is a little bit outdated, so let's close this example and switch gears. Switch gears not so much towards writing code, but from now on, because I only have 45 minutes in total, from now on we will do more of a code walkthrough, okay? So I will walk you through various technologies and techniques, how you can use WebAssembly to combine TypeScript with Rust. So in this example, and I will share the GitHub link of this example in the chat, and of course also with the conference organizers, so you can take my example and take a close look after this talk. In this example, I really updated everything to the newest versions. As you can see, this is latest Rust 2021, and we use a bunch of features which we will talk about in a second. If we take a look in the www folder, when we take a look at the package.json, you will see that I'm really using, I think I updated the dependencies yesterday, so if something is outdated, it happened since yesterday. You see a recent version of Webpack, of the Webpack dev server, of TypeScript, and so on. So this is newer, this is current versions, this is exactly what we wanted. But still, see, this is what I used before in the Hello World sample. We simply reference the npm package that we get out of our Rust code. And then, well, the rest is simple. What I did is I created a small little index.html, and here you see the TypeScript code. And before we go any further, let me quickly show you what's really going on behind the scenes when talking from TypeScript through JavaScript with WebAssembly, which was generated from Rust, okay? First, here you see the first and most important import that we have here. Here we import Wasm examples, which is generated here with the Wasm pack. So what we essentially import is that guy here. That is the TypeScript type definitions, and here you see the JavaScript file. The JavaScript file that is imported here imports the WebAssembly file, as you can see it here. This is the WebAssembly file created from Rust, and here it imports this background JavaScript. Now this background JavaScript contains a thin wrapper around every WebAssembly function that is in our Rust code. Let me show you how that looks like. I'm looking for our greet function. Where is it? Yeah, here, my say hello function. See, for a trivial function which does not receive any input parameters and which does not receive any output parameters, return values from Rust, it's really just a very thin layer, just taking the call and forwarding it to WebAssembly. That's what it is. But if we have input parameters, we will see additional code here. We will see code here where we have to translate JavaScript types like strings or specific number types and so on. We have to translate these types into a representation that WebAssembly and Rust understands. WebAssembly does not rely on the same type system as JavaScript. In fact, WebAssembly only knows a handful of types. 2 integer types, 2 float types, a bunch of pointers and references, but that's it. There is no string in WebAssembly. Just like in assembler, there is no string. A string is a bunch of characters, a bunch of bytes. Essentially what we need is we need to, for instance, encode a string in UTF-8, and then Rust can decode it from UTF-8 into a Rust string and do something useful with it. The other direction is this one after the call. Here we have the return values. We have to turn the return values encoded by Rust and WebAssembly and turn them into consumable types on the JavaScript side. So this is why we have this small layer here between Rust WebAssembly and our JavaScript code. And that is essentially what is generated here by Wasm pack. Okay? So if I scroll down a little bit, we see that here. You will see this method in a second, but let's quickly talk about it, and we have it away from our topic here. This is the core method. And let's use another color here. This is handling of the input parameters, and down here, this one is handling of the result values. So exactly what I told you before. We encode the parameters, we decode the return values, and in the middle we call the Wasm code from Rust. This is why it is important to have a small little nice software robot helping us and generating for us a little bit of JavaScript code to do the plumbing. Okay. So now you understood how this works, and now you know what's going on when we import this Wasm examples here. So now let's take a look at various use cases. Okay, so we have an initialization function. This is not super interesting, but let's first take a look at this one here. So here you see a call to WebAssembly to a method called sayHello. And here you see the Rust method. So this is really trivial. As you can see, we can define a method. Inside of this method, we can essentially do what we want. We can define externally methods which exist in JavaScript land. So we can say there is a method alert, which was defined by the browser. We can also reference, as you can see it here, methods which we define ourselves and make it available globally, as you can see it here. So we can define our own JavaScript methods and call these methods from within Rust. We can access things like console log by defining a name here and defining that this is not in the global namespace but in the console namespace. I think as experienced JavaScript and TypeScript developers, you immediately get the idea, right? And this really works. Let me show you that. So let's run this guy. First we do a Webpack build just to make sure that it really compiles. And that looks good. And then I already started in this guy here. I already started my Webpack. And here you can see this is what I got. And here, if I go in the console, let's make it a little bit larger. If I click sayHello, you see this is calling Rust and Rust calling alert. I can do this one. This is calling Rust, Rust calling my JavaScript method, and my JavaScript method then calling alert. So you see, it works perfectly fine in both directions. That is really simple, and I think we can check that one and say, okay, we understand that. Let's go to the more advanced examples because we only have 15 minutes left. So let's talk about how we exchange data. Let me make that one a little smaller and let's focus on this method here. This method shows you a bunch of use cases packed into a very simple functionality. This is a function, work with numbers, which receives a bunch of numbers. The first one is trivial, it's just a float 64, which will obviously translate in JavaScript to number, of course. The last one is an integer 32, and this is getting a little bit more tricky because do we have integer 32 available to us in TypeScript? Well, obviously not, so this will also be translated to a number. Yep. Then we have something which is kind of odd here. We have an option, float 32. Now you have to understand that Rust relies heavily on the concept of so-called enums. Instead of having a null pointer like C, or instead of having an undefined variable, Rust really has the concept of enums. Let me show you that, because if you're interested in Rust, or I want to fascinate you for Rust, if you take a look at this one, this is the enum option. If you have not worked with Rust before, here you see why Rust really shines. Because an option can be, here, a regular enum, just like you know it from TypeScript, for instance. But some, as you can see it, some enum values can have additional parameters. You see that one? So what option essentially says is either I have nothing in me or I have something in me, and if I have something in me, I can give you this little something here by accessing the sum value of the enum. So an enum is not just a list of values, but it is a list of values and optional parameters which can again be complex data structures or again be enums or things like that. So with the option type, we can say this is an optional parameter. And guess what this is translated to? Let's take a look here. If we go into the package folder and take a look at the DTS, and we take a look at the work with numbers, see that one? So this sample should show you that this is not a trivial translation. It really understands the semantics of the Rust language and tries to translate it to a good fit inside of the JavaScript world. It doesn't fit very nice to float 64 and integer 32 because Rust is very, very powerful in terms of numeric data types. But if you take a look to this one, I returned consciously here an integer 64, which translates to a big int in JavaScript and TypeScript. So you see, this is really an interesting and intelligent translation. Let's go back to our TypeScript here. Here's the TypeScript. And first, I would like to show you localhost 8081, here it is. Let me move that to the right window. Did I stop the web server? Let me see. Oh, it's 8080. I'm sorry, it's 8080. And as you can see, this really works. If I pass in numbers, let me show you the code again. Here it is. What I do here is see, work with numbers. I pass in a large number. I add 1 and I add 1. And the result will be, as you can see it here, 1 and a lot of Fs. Works perfectly fine. And I can also do the same with undefined here in the middle, and it is perfectly well translated into Rust, into the option type of Rust. So this is what you can take away from here. Now, I only have a little bit of time today, so I will skip a lot of the examples here in this demo. But as you can see, I added a lot of comments here. In fact, this sample is part of a larger sample that I created for my multi-day Rust workshop. So if we had a multi-day workshop, we will go through all the details here. But now I have to jump a little bit, and I give you the link to the GitHub repository so you can study the code yourself and experiment with it. I would like to jump to, believe me, passing strings works. Passing slices or arrays, it just works. These things just work. Passing complex data structures through JSON or directly by accessing the data structure elements from JavaScript to Rust, from Rust to JavaScript, it simply works. So these things are easy peasy, they just are there. But I would like to go into a specific example where is it? Here is my example, where that, from my point of view, is the best demonstration of where WebAssembly plus Rust plus TypeScript really shines. And that's the area of compute-heavy work, doing visualizations, doing games, doing charts, doing complex interactions with the user, which is not just an input form. This is where this combination really shines. And of course, for a 45-minute talk, I cannot do a super complicated game engine or whatever. That's not possible, and it wouldn't make sense because that is just too much. I did something else, and I did something which reminded me of my childhood. Who else in the room is of similar age like me and loved Knight Rider when you were young, right? This kid, this sonar going left and right and left and right. And what I thought is, wouldn't it be funny to use that one as an example for a complex visualization? Now you have to use your imagination, of course. Instead of this Knight Rider animation here, imagine that this is really a complex visualization of medical data, a game, a computer-aided design system where you visualize a complex building construction to an architect, something like this. In our situation here, to really prove the point and to understand what's going on, I use this rather simple animation here, and I would like to show you how this is typically implemented when you use Rust for doing the heavy lifting calculations in the background and using JavaScript for painting the pixels on the screen. So let's use that one as our last demo. Let's first take a look at the Rust code. As you can see it here, the main structure in our Rust code, I will zoom in for you so you can see it a little better, is this one. I called it the display. The display consists of pixels, and these pixels are a vector of 8-bit values, unsigned 8, so we have a vector of bytes. Now you have to understand, a vector is really similar like a JavaScript array. It's an array that can grow in size, it's not constant, and you can read and write elements from it. That's a vector, okay? You can push things in it, you can pop things in it, you can access it via index and things like that. Now every single pixel has a value between 0 and 5. Imagine that this might be a LED strip, then this is the intensity of the LED, of the light that you have that you control here. But in our case, it's just the light intensity. If you use the HSL color scheme, hue, saturation, lightness, then this is the lightness factor. Okay, so this is what makes our pixels shine. And then we have a direction whether the Knight Rider animation is currently going left or going right. It depends. Now the code itself is not that difficult, and I don't have the time, unfortunately, to dive into the Rust code here, but I think if you are an experienced JavaScript or TypeScript developers, you will probably be able to guess everything from the context. You see, first we have a constructor function which returns display. The display is the data type that we had up there, and we just initialize everything with 0, and the leftmost pixel is set to max intensity. That is our starting point. Now let's jump over this one here and go to the next method. The next method is really executed regularly, typically whenever you have to refresh the screen. So request animation frame could be a typical starting point for next, or in our case we simply do a timer where we do every, I don't know, 50 milliseconds or so, where we call next. Next is essentially doing the heavy lifting, really the computational work. Now you have to use your imagination here. All this thing here, this is really trivial. It's just taking a look, where is the reddest, the most intense pixel, moves it to the left or to the right depending on the direction, and change all the other pixels to the left or to the right depending on the direction. Very trivial algorithm. But this is where you would put your complex calculations. This could be your complex route calculation for a logistics application. This could be your visualization stuff. This could be the game engine. This could be whatever you have to do, what's crunching numbers. Even if you need multi-threading, multi-threading is, at least in most browsers nowadays, very well supported, and you can use multi-threading with special libraries in Rust directly here in WebAssembly. So this is where the numbers are crunched. Okay? Now, how do we communicate the results with JavaScript? This is where this little guy comes in. What we essentially do here is we are asking the vector in Rust to give us a native pointer. This is a native pointer into the linear memory of WebAssembly. And the beauty for TypeScript and Rust and WebAssembly is that that TypeScript can access this memory directly without having to ask Rust to do that. So on the TypeScript part, this looks like, where is it? Here is it. This looks like that. Here we generate the display, and here, see, we are wrapping the JavaScript type uint8 array. Yeah, this is a byte array. We are wrapping it around the memory that was allocated in Rust land. So we have a sequential amount of bytes in WebAssembly memory, and we can write to it. Here you see how we write to it in Rust, and we can read from it in JavaScript. Here you can see how we read from it in JavaScript. And then everything I need is just a little canvas in HTML, and I can simply do something like a rectangle or drawing the pixels on the screen. And the current value of the pixel is simply read from the WebAssembly memory. So here you see a typical use case for the combination of TypeScript and Rust. Rust is doing the calculation, and WebAssembly, of course, is doing the calculation. JavaScript is interacting with the browser DOM and painting the pixels on the screen. Now, obviously, this is not the only thing you can do. Yeah, you can do other things, but we have to think about whether this really makes sense. Just for the sake of completeness, you see a little bit of Rust code here, where we do things like get element by ID. Everybody knows that? I guess you do. HTML input element. Does that sound familiar to you? I guess it does. Create element. Or here, where do we have it? On click with a button handler. See that one? So it is also possible to write code that is directly accessing the browser's DOM API. For that, there is a crate which is called WebSys. You can do that. But you can ask yourself, why should I do that? There are Rust developers out there in the world, believe it or not, they don't like JavaScript. I don't understand them. You probably also don't understand them, but there are people on this planet who don't like JavaScript. And they prefer writing code like that in Rust or C# or Go or whatever. And it's possible. But the sweet spot, I would say, is not specifically code like that. So if you know JavaScript and you're not afraid of it, use JavaScript for what it's really good. But when it comes to crunching numbers for doing performant things, if it comes to reusing code that has to run on the server and on a desktop app, then Rust and WebAssembly and TypeScript are really a match made in heaven. And this is exactly what I wanted to show you. And with that, hey, I could talk forever. I could talk for hours and days about this topic, but I hope it was an interesting session. I wanted to inspire you. I wanted to make sure that you understand where the sweet spot of these technologies is. I wanted to make it very clear how it works together, and I wanted to showcase a bunch of code snippets that make it easier to understand how this combination works. And with that, I give back to the moderator and ask whether we have any questions from the audience.